Hey guys, welcome to Exponential Functions. So, really simple, we're going to start off with what it is, and then we're going to talk about its similarities to some other functions. We're going to talk about how to deal with it. We're not going to really get into a ton of kind of solving equations type with it until a couple lessons from now. We're going to do some logs next, and then we're going to combine logs and exponentials because that's how we solve these things. So, what is an exponential function? Well, the general form of an exponential function looks like this. C times a to the x. Now, you may have done it in the past where it's like a times b to the x or whatever, but c times a to the x is the variables we use. So, what's really important here is to recognize that c is the starting value, okay, or similarly our y intercept, okay? So this is the point at which our function crosses the y-axis. Okay, really nice. A is something that we call our growth factor. Okay, our A value here can determine our decay rate or our growth rate, and we'll talk about that in a minute. But that's really nice and simple. Now, there's some conditions we have on these functions. Okay. Similar to like polynomials and things like that. With a polynomial, we said that leading term, that leading coefficient, couldn't be 0. We have some similarities here. And that one of the similarities, one of our conditions, is that c cannot be 0. If c is 0, we get 0 times a to the x, which that just makes everything 0. Function is a constant function 0, that's not an exponential function. Now c can be negative, and if it is, basically what you're going to do, for pretty much the entire lesson, we're going to talk about c being positive. If c is negative, just flip everything. So in other words, instead of it going up like this, it goes down like that. Because all that c being negative does is give us a vertical reflection. So another restriction we have is that a has to be greater than 0. Now notice it's not greater than or equal, okay, but strictly greater than. If a is negative, what happens here is we get this really crazy function. It bounces all over the place, depending on what x is. Because let's say a is negative 2. Well, negative 2 to the first power is negative 2. But negative 2 squared is 4. Cubed is negative 8. To the third power is positive 16. And so we get this bouncing back and forth that doesn't really work as a function. Also, if x is, say, a half, we don't know the square root of negative 1/2, of negative 2. So negative 2 to the 1/2 doesn't work. Now there's another situation, there's one more rule we have, and it's that a cannot equal 1. And the only reason why is because 1 to any power is just 1, so we just get the constant function c. Kind of the same reason why c can't be 0. These two things just give us constant functions, and they're not exponentials. So that is our general exponential function, and this is our restrictions on that. Okay. Now, there's another special form of an exponential function that you'll see occasionally, especially in like science and stuff like that. And it's typically done, measuring some amount of something like that is typically where it's used at, or some populations, so I'm going with an A. And it's almost always done on a time function. Okay, which means the inputs are measurements of time. And this just looks like c e to the k times t. So here we have three constants. And you may be going like, well, last time we had 2, now we have 3. Why do I want to use this? There's some benefits to using this. And first things first is, what is e? So e is approximately 2.718, and this is a number. It's an irrational number, like pi. This number goes on forever, never stops, never repeats, can't be written as a fraction. Okay? This is a very special number that comes up in math all the time. We're going to use it a lot on your calculators, so for you guys who want to be able to use it. Okay? There's the button right here that says ln, and the secondary button above it, e to the x. So that's what you're going to use. So if I want to figure out, say, what is e equal? Right? In our calculator, just get second ln, we get e to the x, and we just want to make it e to the first. And hit enter. 2.718281828. Now it may look like it forms a pattern there, but it doesn't. That pattern breaks off. So this is actually a number. It's a fixed number. It doesn't change. C and K are our only unknown constants, just like when we had the general form C times A to the X. Again, C is the same thing, and that cannot equal 0. The thing is, though, since E is this 2.718, what we can kind of do is we can think about this, and using exponent rules, I can rewrite this like this. C times e to the k, let's make that a k, e to the k, all raised to the t. Because we know if I have a number raised to a power raised to another power, the way we combine those exponents is by multiplying them. And so these are the same thing. And so what's cool about that is it makes it so our restrictions on k is only that k can't equal 0. If k equals 0, anything to the 0th power is 1, so we get basically where the c times 1 to the t, and that's just c. So those are only two restrictions on this kind of alternate exponential function. Okay. So there's our two forms of an exponential. We have the general form, which is what we're going to use for the most part of this class. Unless I specifically state to use this, don't. And we're definitely not going to really use it until after we cover logarithms. Okay. Now, the homeworks for these two sections, exponentials and logs, extend past when we're going to cover all of these. So you may need to use some logarithms to solve some problems in the exponentials homework. It may make some easier and stuff like that, and vice versa. And so, the idea is that the exponentials homework is going to cover things that you may need logs for. Just wait until after we cover logs. So, we have our two forms of an exponential. Now let's talk a little about it. So, what's really cool got two functions in here. Fx equals c times a to the x, that's our exponential. And what's this function? What type of a function is this? Absolutely, right? That is a linear function. G of x equals m times x plus b. A good old-fashioned slope-intercept form. These two functions are extremely similar. There's one difference, actually, between these two functions, and that's it. I mean, overall speaking. And that one difference is that the way they change. A linear function, think about it. Every time x goes up by 1, we add our slope, right? Over up, right? And so this one changes additively. In other words, every time our input goes up by 1, we're going to add some amount. Whereas an exponential function changes barely fitted in there. This changes multiplicatively, which means every time x goes up by 1, we're going to multiply by a fixed amount. And in this case here, that amount is a, which is really cool. So back to linear functions. So I'll kind of draw a line here since I got those down so close. In a linear function, our rate of change, in this case, our additive rate of change is m, our slope. So m is instead of writing additive, I'm just going to write this like a plus, is the adding rate of change. Now, I don't want you to confuse this with like average rate of change. That's not what we're talking about. We're talking about m is the rate at which we add by each time. But for an exponential function, a is the multiplicative, right? So the multiplying rate of change. In other words, in an exponential function, every time x goes up by 1, we're going to multiply our previous output by a. And we're going to do an example where we'll see kind of a table of how this happens and what that looks like. Okay, both of these, just from looking at the equation, we know the y-intercept. This, the y-intercept, is c, and here the y-intercept is represented by b. Okay? So we have a lot of similarities between these, right? The big difference is that an exponential function changes multiplicatively, where a linear function changes additively. Okay? So pretty cool. Now, let's give myself some more room so I'm not writing all the way down on the floor. So our A and M, we're going to focus on those kind of those growth factors, that change factor kind of thing. With slope, we know what that does, right? What does slope tell us? If you think back to linear functions, right? I know it's a while ago, we've covered a lot, but linear functions, that slope, that m, if it's positive, our function is increasing, and if it's negative, it's decreasing. So that's really cool. So if m is greater than 0, increasing. If m is less than 0, decreasing. And in much the same way that our kind of m, that additive rate of change, tells us whether we're increasing or decreasing, this a, our multiplicative rate of change for an exponential function, tells us whether our function is increasing or decreasing. Now, we don't say increasing or decreasing with exponential functions. We say whether we have exponential growth or exponential decay. Means the same thing. Growth is obviously going up, decay is going down. So our restrictions on a, if we remember back, a had to be greater than 0, and it couldn't be 1. So it gives us a nice little split. We've got everything that's between 0 and 1, then everything after 0, after 1. And so what we say is if m is greater than 1, what's happening, every time x gets bigger, say every time x goes up by 1, I'm multiplying by a number that's bigger than 1. So that's making things get bigger. So if a is greater than 1, then we have exponential growth. And graphically speaking, it looks like that. Okay? Now, however, if 0 is less than a is less than 1, then we have exponential decay. Which looks like that. Okay? So just by looking, so just like a linear function, if I just looked at the equation, I could tell you is it increasing or decreasing, by how much every time, and what's the y-intercept, right? So if I say g of x equals 3x plus 5, I know that my function is increasing because the m is positive. I know it's increasing by 3 every time x goes up by 1, and it starts at the point 0, 5, right? Now, I don't want to write it down there. I'm going to write it over here because I don't want to squat down. If I have fx equals 5 times 3 to the x, okay, this function, because our a value is greater than 1, we have exponential growth. I know that every time x goes up by 1, my output gets multiplied by 3. And I know it starts at 5. So all of that I know just by looking at the equation, without doing any work whatsoever other than identifying if it's greater than 1 or if it's between 0 and 1. Just looking at it, I know all of that. So now let's look at a couple of tables of functions and see kind of how those growths work. Let's just stick with what we had. Now, what we know with both of these is they both start at 5, right? Because the c is 5 here, the b is 5 here. So we know both of these start at 0, 5. Now let's go with the linear. Let's start with the linear because that one we were comfortable with, right? Every time x goes up by 1, we add 3 because our additive rate of change is 3. So x went up from 0 to 1, so we add 3. So we go from 5 to 8. From 1 to 2 goes up 1, so we add 3. So we go to 11. Now what if I wanted to skip 3. What if I go to 4? Well, it means that going from 2 to 4, I didn't go up 1, I went up 2. Which means I need to add 3 twice, and adding 3 twice is just adding 6, so we get 17. We do the same thing with any jump, right, from anywhere, right? What if I want to jump from 3 to 6? Well, to jump from 3 to 6, I add 3 1, 2, 3 times, which means I need to add 9. So it's 23. Okay? So that's pretty easy, right? Pretty cool. Now, over here, every time x goes up by 1, my multiplicative rate of change is 3. So I'm multiplying by 3. So when x goes from 0 to 1, I take 5 and I multiply by 3 and I get 15. When I go from 1 to 2, I multiply by 3, so I go from 15 to 45. Now, I want to make sure I get these right, so I'm going to my calculator, because I am not a mental calculator. Now, what if I wanted to go from 2 to 4? Well, I need to multiply by 3, and then I multiply by 3 again. So what is that multiplying by? It's not multiplying by 6, right? Because adding 3, that's adding 6. But multiply by 3, that's actually multiplying by 9, because we multiply by 3 times 3. So 45 times 9 gives us 405. And finish filling in that table. We get that. So what's really cool is looking at this, we can figure out some things, right? If we didn't know this, let's say we didn't know what that was, I can see, well, okay, to get from here to here, I either added 10 or multiplied by 3. To get from here to here, I either added 30 or I multiplied by 3. Well, adding, that wasn't constant, right? So it definitely can't be linear, right? Because it's not like I add 3 and then I add 10 and then I add 5 and then I add 7, right? We add the same thing every time. So this can't be linear, but I multiply by the same thing every time, so it must be an exponential function. So I know that since I'm multiplying by 3 every time, my a value is 3. Since it starts at 5, my c value is 5. So from a table, we can actually figure out a lot if we know that it is either linear or exponential. Okay? It's pretty cool. Pretty nice stuff. Now, just like a linear function, if I give you 2 points, you can create the equation that goes through those 2 points. We can do the same with an exponential. However, there's 2 different cases. There's the case where we are given our y-intercept, okay, and then there's a case where we're not. So if we're given our y-intercept and we want to find the exponential, so our goal, find the exponential, goes through 0, 7, 3, 1, 89. There's a really simple process to this. The first thing you always want to do, anytime you're finding a function, you want to write the general form if you can. So I'm looking for the function that looks like c times a to the x. Do I know c or do I know a? Well, since we're given our y-intercept, I know what c is. So that means I know my equation is 7 times a to the x. So we need to figure out a. The way we do that is using this other point. So I use this point where we have this x and this y to create an equation with what I know. So what I get is I get the equation 189 equals 7 times a cubed. So I replaced my x with the 3, and I replaced my output with 189. Now this is just an equation that we can solve. Okay? I need to divide both sides by 7, giving me a cubed equals 27. Now at this point you may be like, I know the answer, let's go, woo! But that's awesome. Let's talk about how we get through it. That way, in case next time you don't know what to do. There's two things you can do here. Both are actually the exact same thing. So I'm going to write this a separate times on the side. So both of these two things that I'm going to do are really just doing the exact same thing, just in different forms. So one of the options, because I have a cubed, to get rid of that cubed, I could cube root both sides. Okay, those cancel. A equals, and we can use our calculator to do this, and we get A equals 3. The other option we can use, and this is a bit more calculator friendly of an option, and again, it's the exact same thing, is I can raise both sides to the 1/3 power. So a to the third to the 1/3. Remember what I said earlier on in this lesson, right? If I have something raised to a power, we multiply those exponents. 3 times 1/3 is 1, so this just becomes a. And 27 to the 1/3 becomes 3. Now, I'm going to change my mode here real quick. So if you have an older calculator, and what I mean by that is, if when you hit, say, the exponent button here, if you get something that looks like this, okay, you have to be really careful here. You have to be really careful. When you do 27 to the 1/3, if I just type 27 to the 1/3, gives me 9. What happened? Well, what happened there was it did 27 to the first and then divided by 3. That's not what we want. What we want is 27 raised, and then so you're going to need parenthesis 1/3. And that gets the right answer. Okay. Now if you have a newer calculator, so that when you hit that exponent button, it just puts you up in there, then you just type 1/3, and you get the right answer. So, make sure you're aware of what type of calculator you have, what type of issues you may have with your calculator, and kind of the approaches to go. So we now know what our A is, so we go back to our function. This is 7 times 3 to the x. That's it. So if we have the y-intercept, okay, step 1, put in your value for c. Step 2, to create an equation, solve for a. Step 3 is give your final answer. It's pretty easy. Okay. Now, if you want to break that up a little more, right? C equation, solve for a is a separate step. So you've got 1, 2, 3, 4. I don't remember on the lecture guide earlier I said 3 or 4 steps. So that's the easy case. Now, what if you don't get the y-intercept? If I don't get the y-intercept, we're going to do something that looks a little weird, but is really something we've done a long time. Now, we're going to hold off on that. I'm going to do a little demonstration for you. If these two facts, if I know these two facts, if A is equal to B and C is equal to D, is this true? Is this statement true? A over C is equal to B over C, assuming C isn't 0. Okay. Well, I mean, it's like, how would I know about it? Then it's like, well, all I did is I took this equation and I divided both sides by C, right? We can do that. We can divide both sides of the equation by something, and as long as it's not 0, we're good, right? Perfect. So that works. That's true. What about now? Is this still true? So now I have a divided by c is equal to b divided by d. I didn't divide by the same thing on both sides because I divided by c over here and d over here. But I know that c and d are equal. So since they're equal, this is still equal. So this is still true. Okay? This is what we're going to do to solve an exponential function if we don't have the y-intercept. And what we're going to do is we're going to choose the correct kind of c's and d's so that things cancel out nicely and things look good. Okay? So, let's do a problem. A bunch of you guys are like running scared right now. You're like, oh my god, there's negatives and fractions. It's okay. We got this. Okay? Scary numbers are still just numbers. They're our friends, right? No number discrimination. Everyone's nice. So, the first thing we need to do here, right? I mean, obviously, right, we know I'm looking for the function form ca to the x. I don't know either c or a. So the first thing I want to do is I want to create two equations. I want to create my a equals b and my c equals d. And the way I do that is I use these 2 points with this general form. So this first one says, if x is negative 2, it equals 12. So I get 12 equals c times a to the negative 2. This one here says, if x is 2, I get 3/4. So this gives me 2 equals c times a to the 3/4. Sorry. That's wrong. 3/4 equals c times a squared. That would have been a very different problem. I'm not going to give you a problem like that. So, we get something like this. So that's our first step, create two equations. What's the next thing? Well, I want to divide one of these equations by the other. I want to create that a over c equals b over d. And I want to do this in a way that things cancel out and work out nicely. So what I always want to do, and you may have been like, okay, this is my a equals b, c equals d, right? But scrap that placement for a minute. Always, okay, big red letters flashing like, hello, always, always take the equation with the higher exponent and divide it by the equation with the lower exponent. The reason why is because you will always, if you do it that way, you'll always end up with an a to a positive number. A to a negative number is still solvable, it's just a lot more mess, okay? A to a positive number makes things a lot easier. So I want to take this equation here, since it's got the higher exponent, and divide it by this equation here. So what I get is I get 3/4 divided by 12 equals ca squared divided by ca to the negative 2. So what happens here is a few things. One, 3/4 divided by 12. Okay. Gives us 1/16. Don't ask me why that took so long. I just hit wrong buttons. And then what happens on that right-hand side? Well, I've got c times this a thing and c times this a thing. So those c's cancel each other out. And now we have to remember, how do I combine these exponents? If I have the same base raised to a power divided by that base raised to another power, we subtract the exponents. So what I get is I get a to the 2 minus negative 2. So I get a to the 2 minus negative 2. So that just gives us a to the 4th. Okay. Then we can either raise both sides to the 1/4 power or take the 4th root of both sides, just like we did on that last problem. Okay, so let's just do the 4th root. We get a equals 1/2. Okay, so that's a lot. Let's kind of go back over. So first step was to create our two equations. Okay, then we took the equation with the higher exponent, divided it by the equation with the lower exponent, and we solved for a, right? Our c's fell off, combined our exponents, and then we just took the roots. Okay, so what I now know is that my equation is c times 1/2 to the x. From here, you can do either equation. So what you're going to do now, so step 1, create two equations. Step 2, divide the equations by each other and solve for a. Now I want to look at these two equations, and I want to plug in my a value into one of these two equations. It doesn't matter which one you do, right? And especially in this exact example, you've got a negative exponent here, you've got fractions here, whichever one you're less scared of, I guess. I like to deal with positive exponents whenever possible. So what I end up with is the equation 3/4 equals c times 1/2 squared. I can solve this for c. Right? The first step is, what's 1/2 squared? One-fourth, right? 1/2 times 1/2 is 1/4. Now, how do I get rid of 1/4? Well, I could divide by 1/4, but that's just the same as multiplying by 4. So if I multiply both sides by 4, these cancel, and I'm left with c. And on this right-hand side, the 4's cancel, and I'm left with 3. So that gives me a final answer of 3 times 1/2 to the x. So the exponential function that goes through these 2 points is 3 times 1/2 to the x. Okay? Mark it down in your calendars. Guarantee you 100%. This will be on the final. Okay? Now, you may be like, oh, cool, well, I know other tricks to find that exponential function through this with. I'm going to ask you things like, what are the two equations? And do some things in between, so you have to do this process. You can't use regression to do this for you. I'm tricky that way. So, that's it. Step 1, create two equations. Step 2, divide one equation by the other, right? The higher exponent equation by the lower exponent equation, and solve for a. Plug that back into one of those two equations and solve for c. And then say your final answer. That's it. That's how we do these. They're really not too crazy. They're not too complicated. So I want you guys to get some practice doing these, right? Make up points and check them in your calculator if you want to. Do the homework. If you have any questions on this, always shoot me an email. Okay? So, move on. Exponential functions are really useful in a lot of different areas, but one of their biggest applications is in finance and money. Okay? And what it is it's actually used for calculating interest rates. Now, you may have done problems before where you've had like $5,000 invested at 3%, and you've had it in there for 10 years. You're like, okay, cool, that's like 5,000 times 1 plus 0.03, the decimal is the percent is a decimal, and then raise it to the 3rd power. That's one type of interest. That is called annually compounded interest. We want to talk about something called periodically compounded interest. So, first of all, what is that? So, periodically compounded interest. This is simply when interest is calculated multiple times throughout a year. And it can be beneficial to you if it's gaining money, so it's like a savings account. It can be detrimental to you if it's something like a credit card. So knowing whether your interest is compounded monthly, weekly, daily, yearly, whatever, is really important when you're doing finances and doing financial things later in your life. So let's talk about this situation. Let's build a function. We're going to build an equation that can calculate the periodically compounded interest. Okay? We need to have some variables defined first. So P, right, which we say is the principal amount or anything like that, but this is what we just say is the initial amount. So if you invest $5,000, P is 5,000. Okay. Now this formula only works in the simple setup of you dump some money in, walk away, and leave it for years. Okay. So I like to call this the lottery scenario. This is where you win the lottery, you throw $10 million into a bank account, walk away until you retire, never add to it or take from it. Okay. The next thing is R, and this is the interest rate as a decimal. It's very important to recognize we never do math with percents, ever. Math is always done with decimals. Let me back up. You can do math with percents, but it's usually like we say this thing represents a percent, so then when you calculate it, it gives you 95 instead of 0.95. But when we're given like percents as interest, so just, for this purpose, always convert to a decimal. And the last thing is N. This is the number of compounding periods per year. The number of compounding periods per year. So this is simply how many times in 1 year is the interest calculated. Now, when we're doing this, there's a couple caveats I want to make. First of all, there's 1 year in a year. There's 12 months in a year. There's 52 weeks in a year. There's 365 days in a year. Now, that's the one where I get people going, well, and that's, by that person, I mean, the one who wants to challenge things because they're bored. I know there's 365.25 days in a year. If you want to say, well, what about leap years? There's an extra day. Well, that's where that 0.25 comes in. But for the purposes of the calculations within this class, if something is done yearly or is done daily, it's 365 times in a year. We're going to ignore that leap year. We're going to ignore that 0.25 of a day. 365 for days in a year. So, given that information, okay, the way we can find the amount in the account after T years, we say that A of T equals the principal amount times the quantity 1 plus R over N. Okay. So our interest rate is a decimal, divided by the number of compounding periods per year, all raised to the n times t. So this is our periodically compounded interest formula. Okay? If it's $5,000, we'd have 5,000 here. 0.2 is, say, 5% interest, 0.05 here, compounded monthly. So there's 12 months in a year, so we'd have 12 both in those spots. And that's our function. Okay? So these are the three things you need to identify. These three guys are here. These three pieces, identify what they are from the problem. These will be given to you in the problem statement. Okay? Once they're given to you, then you can use them to plug into here. Okay? Now there's one other possibility. So this is periodically compounded. It could go all the way down to seconds. It could go down to milliseconds. But what if it's done continuously? In other words, it's infinitesimally small moments of time, right? It's just continuously compounded. I like videos because I can just do that and you have to pause it to write it. So, continuously compounded interest. we still have the same P and the same R. We just no longer have the N. And for the amount in the account after t years in a continuously compounded interest formula, it's just simply P times E to the RT, where this E is, again, that E button on our calculator. This is that 2.718. Told you it comes up a lot. This is our formula for continuously compounded interest. Okay? So these problems are so incredibly easy. I don't want you guys to get crazy worried. If you guys get stressed out about these problems, you're not stressed out about the math of them, because the math of them is going to be really simple. It's going to be like, you're invested this much at this rate, compounded this often, how much is it in 15 years? Okay? Or after we do logs, I can say like, well, after how many years is it this much? The hard part of this is pulling that information, and that's just something that really just takes practice doing these problems. Okay? So, start practicing, and I'll see you guys with logs.